Dr. Etienne Bernard has been leading the machine learning group at Wolfram Research for the last 5 years. At Wolfram, he's worked on developing automatic machine learning tools, a neural network framework, and machine learning applications for the Wolfram Language and Wolfram Alpha. Before entering the machine learning field, Dr. Bernard obtained a PhD in physics from ENS Paris and worked as a postdoctoral scholar at MIT, where he designed Markov chains Monte Carlo algorithms to solve physics problems. Now, without further ado, I will let Etienne take the stage and share with us all his knowledge.
All right. Thanks, Erez. Okay, let's start. So, and of course, yeah, thank you for inviting me, and thanks everyone for coming here, listening to me. I hope I'm not going to waste your time. Apologize for my casual look. I don't realize it's true. It's an actual seminar that is displaced. I should have dressed accordingly, but anyway, sorry about that. I'm at home. Okay, let's share my screen. I hope that you can all see it. And by the way, so this is a notebook, and I'm going to edit this notebook during the presentation. And you can, but I'm going to save it regularly. Actually, let's save it right now. It's on a Dropbox, so you can get it at this link. And even after the presentation, I will let it for, I don't know, months. You can always get it in its final form after. So actually, let me
that
put it
link's in the email we sent out.
Oh, it is in? Okay, I'm adding it back in the chat. All right. Okay, so let's start. So yeah, I'm going to talk about kind of the machine learning functionality that we have in Wolfram Language. I gathered you already have a bit of you had some presentation about the Wolfram Language, and Stephen Wolfram came and talked to you about it. So I'm not going to assume you know the gist of it. I'm going to assume you know a little bit about what machine learning is, but I don't think it's that necessary. Okay, so mainly there's two parts in this framework that we've been developing in my team this last 7 years. One is about an automatic machine learning framework. So basically, I mean, actually, I'm going to explain that after. Yeah, an automatic machine learning framework. And another part, so this is really to do things without being an expert necessarily, or to do things faster. It's good to do baselines. It's good to do unstructured data also. It's the best unstructured data. And then there's a neural network framework, which is a little bit more for perception tasks like vision, audio, text, these sort of things. And it's a little bit lower level. Like, you know, you can manipulate the network. You can do all sorts of things. So you need to have a little bit more expertise to do this than automatic machine learning, of course. And then I'm going to talk about some applications that we did using these tools, basically. So kind of some real life example. And generally, this application, we put them in the Wolfram Language as well. So you can actually use them. All right, so automatic machine learning. Sorry, the Zoom thing. Oh, that is annoying. Let me put it. I'm going to remove it. So I'm not going to see anyone, but that's fine. Okay, so the automatic machine learning, once again. Let's do like this. Yeah. Sorry, I'm sitting at the Zoom. Doesn't do what I want to do. Oh well, that's okay. Okay, so these are a set of functions in the language that are very task-oriented. Like classify is a function to automatically create a classifier, and that learns from data to a classifier that then you can use on other data. Predict is the same thing, but for regression. So it's to predict a numeric value. And find cluster is to do clustering, and there's a bunch of functions like that. And they're automated. So what does it mean? It means that it means that the data that you feed in, the type of data will be figured automatically. The pre-processing will be done automatically. How to extract good features, and of course the type of model that is chosen and the hyperparameter that are used are also figured out automatically. It has to be robust to dirty data, such as if there are missing values. And there is also some control that you can give to this function. such as some are high-level specification, like I want you to give me a model that focuses on being small in memory because I'm going to use it in some embedded device, let's say. Or I have only 4 minutes for you to train this model. So that's your goal, time goal 4 minutes. But you can also specify methods and hyperparameters if you like, and all sort of things. Like we try to have a tool that can be both used in a full automated mode and also where you can a little bit play with the parameters, which is I think the goal that every framework should have really. Okay, so let's show an example. I'm going to scrape some images. So lately I'm into mushrooms. So we're going to create a mushroom classifier. So 4 types of mushrooms, and I'm going to do a web search with web image search where I'm adding the mushroom in the search, to make sure we have mushrooms, because I guess parasol can be many other things. I think the other one are only mushrooms though. Let's do it. So that's a class. Okay, I'm going to scrape for all classes. It uses the web. I have to connect to the cloud. All right, should be good, huh? And I'm going to download 30 thumbnails. Actually, we don't need to have big images. Some thumbnails will be fine. So yes, 30 of them for each class, so 120 in total, which is a rather tiny data set for image classification. But that's fine because Classify, as I will explain, maybe show after, does some feature extraction. So there's already good features for images that are extracted from the data and that allow us to train a classifier with that tiny amount of data. So here I split the data into 80 examples for training set and the 40 remaining for test purpose. So we're training on the training set. And as you see, I didn't specify anything in that case, no method, no preprocessing, nothing. So it's training, and you can see okay. So you could see a learning curve. Actually, we can look at it again. So there was a sort of information panel during the training. That kind of show us, the method that is the best, the expected accuracy and things like that. I'm going to explain that in more detail after. Okay, so now we can just use it on new data. So let's take an example that was not in the training set. That's important. Oh, there's 2 mushrooms. I wonder if that one you get correct. Yep, you got this one correct. We can also ask for the probabilities. So you see, I should have explained, this return a classifier function. So that's our model. That's our little program that can take an image as input and return the class as output. So this is just the class that is predict. These are the probabilities. So it's pretty convinced it's a parasol. We can try with another one. Ooh, this one is not great. Let's see if it works. Yeah, it works. Okay, pretty confident it's a chanterelle as well. So to analyze if a model is good or not, the usual thing is to use a full test set with usually more than 40 examples, but let's do it with 40 examples. So this is better than trying things one by one, of course. So I'm using the function classifier measurements. The first argument is classifier, and the second one is a test set. Oh, I should have told you. Sorry. It's been a while I didn't give a talk. So the training data. I'll show you what the training data look like. So let's take the first 10 examples of the training data. Okay, that's what the training looked like. That's what the classify saw to train this model. So it's a bunch of images and they are tagged with this rule. Okay, so this is the chanterelle, this is the bolete, this is the morel, and so on. And so classify, I gave this to classify, and from this example of classification, learn a classifier that can work for new images. And now we can give it new images, and it got things correct. So let's see the measurements. So you can see a bunch of information. For example, there's about 85% of accuracy in this test set. It means that 85% of the examples are correctly classified by this mushroom classifier. And you see other information like it takes 1/5 of a second to run this model. Okay, great. Yeah, 5 examples per second makes sense. You can see this is called confusion matrix. That's very useful tool to analyze the performance of the model. So, by the way, if you want to ask questions in the middle, I think that's fine. I'll try to answer them without disrupting the talk, but don't hesitate if you have a question. I might I might forget to say something important, and so yeah, don't hesitate. Okay, so here I'm using this classifier measurement object. So this is a report, but it's also an object. So I can kind of query properties to it. So I query this property, so we can see it a little bit better. And this tells us the number of a given example that are classified as something else. So this means that 8 bolids have been correctly classified, but there's 2 bolids that has been classified as parasol. And so if it was a perfect classifier, of course, it will be a pure diagonal thing. And if it was very bad, there will be, some red everywhere. Okay, so for example, let's look at them. Let's look at these 2 bolids that are classified parasol. So I'm going to ask examples, and then I'm going to say bolid, and the second one is parasol. Let's see. All right, that's a 2 example. They are indeed bolids. So clearly that our model is not good enough. We should use more data, or use neural networks, or do something like this. Actually, afterward, we're going to do the same thing using a neural network. You'll see. Hopefully, we obtain better performance. So because sometimes actually it's the data that is not good. So these tools to explore particular confusions, or this one is useful. Okay, best classified examples. All right, that's the one that are very well classified. This means that the probability assigned to the correct class is very high. We can do the opposite, which is more instructive actually. Let's ask the example that are misclassified, but also for which the probability of the correct class is the lowest. Like you really did not believe. So this one, for some reason, it did not believe it was a chanterelle. So let's see, mushroom, top probabilities. Okay, is certain it's a parasol. Okay, there's something wrong here. So yeah, so these are tools to diagnose where your model is wrong. Okay, let's deploy this model, even though we've seen it's not that great. So we should definitely not use it to make decisions about whether we should eat this mushroom or not. In any case, it's only 4 mushrooms, so it's not very made for that. So to do that, I'm creating a form function. I don't know why. Let me see. Why does it show red? That's strange. Okay, anyway, let's forget about it. All right, we just do a function where we'll return the top probabilities. And now I'm deploying this form to the cloud. And so it should take a bit of time. I should get a URL back. Yep. And I can shorten it if you want, but now we have a chat. So actually I can just send that in a chat. Maybe we should not all click on it right now, but let's see if it's, we could, why not? So, okay, so if I click on it, yeah, that's a simple form, and it's basically this model that is deployed to the cloud. So I can give an image. So I don't know how we can do that. Let's grab up. Let's do a new window. Oh, actually, that's fine. And let's grab a morale. All right. Morale. I'm going to up. Hopefully, this was not in the training set. If it was in the training set, that would be cheating. And I think I can just click and found it. Yep, that was, no, it was my test example of yesterday. Well, it doesn't matter. That's a moral. Up, submit. And morale 99.7% of chance. So it's pretty confident it's a moral. Great. Of course, I didn't, worked on how it should look, but you have kind of web design tools to make this look the way you want in the language as well. Okay, so we got the data, train a classifier, tested it, and deploy it. That's basically the step that you need to do to for a machine learning project to create a classifier. Any question about that? Okay, let's continue. All right, so automation strategy. Okay, not the most important thing, but if you're curious, that's how it works underneath. There's kind of tools to do, to create preprocessing pipeline, these sort of things. There's also some like automatic conversion, because if you gave data that is, I don't know, nominal sequence, and then the user specify, I want to use this method, and this method only works with numerical vector. Well, there need to be some automatic conversion. So this is kind of the graph we use to automate. So you have the type in red, and in blue it's different processors, and that's how it converts type automatically. That's one of the many little things that we need to have to make this automatic. And otherwise, the way it works is actually rather intuitive, is that it starts with a bunch of possible configurations. So the configuration is the model and the hyperparameters of the model. The hyperparameters are kind of the options of the model. It's these parameters that normally you have to set by hand before training. And in that case, you might have 10 configurations. And here you can see the performance for various training set size. So what the automation procedure does is that it starts by training this configuration on small number of examples. And then from that, it tries to predict how well it would perform on the final number of examples. And if someone is predicted, for example, if this configuration is predicted to be pretty bad, then it's not going to train it further. And we save time, because training on a lot of examples takes a lot of time, while training in small amount of training example is very fast. So yeah, there's some things in the literature that are similar. I think HyperOpt works a bit like this. Anyway, it's kind of a custom thing, but similar to existing things. So actually, let me show you a training with more examples. This has 30,000 examples. It's a classic MNIST data set. This is a data set where you have to recognize a handwritten digit. So let's see an example, or let's see 10 examples. Up. All right, so it's like this is a 3, this is a 4. That's a very old classic data set. Now I'm going to train this one, and setting an option time goal goes to 45. I didn't have to set it, but why not? I have 45 seconds, and that way we can also see what's happening. So this is the learning curve. I'm going to talk about it a bit after. So actually, yeah, learning curve kind of show how the performance improves as we add more examples. This is super useful to know if you have a chance to improve things by adding even more examples. Sometimes it's expensive to add more examples. And usually it's not just adding 10% more example. It's a multiplicative factor. It's, you never improve a model by adding just 10%. You improve a model by multiplying by 3 or 10 the amount of training data. And you can use these sort of things. For example, clearly, it's still going up. So not perfect, but at least we have hope that since it's not a clear plateau, let's look with information. Since it's not a clear plateau, this is accuracy, by the way, it means that with more data, we'll probably improve things further. This is the same learning curve, really, but for another metric, another measure, that is a loss function, which actually it's called the mean cross entropy. It's something that looks at probabilities rather than just is it correctly classified or not. Okay, and this, so actually let's look at it live. I'm going to do it again. Train it again. And you can see the experiments that are done. So it starts with small examples, then it upgrades some configuration to larger. Sometimes it comes back, actually. It's not exactly, it comes back to smaller examples to try yet new configurations or to add configuration to the set, the initial set that we have. And yeah, that's basically how it works to find the best configuration. So it's really an optimization, like I mean, yeah. Each model have their internal optimization loop, so to speak, to train their parameters, and this is like an optimization at the high level where we pick the best model and the best upper parameter. And I said 45 seconds as a time goal. We kind of over that, almost 60 seconds. So it should stop soon. It's not a hard constraint. It's like, since it's training, I could stop it actually. I could stop it and get the current best model. This one probably it trains what it thinks is the best on the full data set, and then it will exit. Okay, fully it's gonna exit there. But anyway, let's stop here. All right. Okay. Okay, so the nice thing of doing this automation is that we have a progress bar, and we can interrupt, we can specify training time specifications. So it's not the only way to automatize machine learning, but I like this byproduct and get the learning curve. I think this learning curve are so useful to decide what to do next. I wrote a blog about that, by the way, if you're more interested. Okay, another function. There's several functions that work like that. That's just another one that I like. Because it's about learning the distribution of data. So let's do it. That's an example of a structured data set, right? It has kind of a some features, and usually their values are either numeric values, like here that's the age of people, and here that's some other attribute about these people. It's a data set about Titanic passenger, also a very classic teaching data set. So you can see that this woman was 29 years old, first class, and she survived. And this poor baby was first class, female, died. It was actually pretty rare. Normally babies survive. And generally it's more the young male, 30 years old male. Anyway, let's not go into the Titanic history. So I'm going to learn the distribution. Why not? Let's set a time goal. Then we can see what's happening. And again, we have a learning curve. This is not the accuracy, it's something else. And if I click there, I should be able to see also the configuration. You can actually see which configuration. This is a multinormal distribution with a specific covariance type. You can analyze afterward. So this allows a bit of interactivity with the user. I like that you can look, like here you go. This was the kernel density estimation with a Gaussian kernel, blah, blah, blah. So if you think, oh, this one was stopped, but actually I believe it would work well given this graph on the full data set, then you can specify it with a method option and retrain it. Okay, so once you have a distribution, what can you do? Three main things. One is about, actually, let's put this one last. Okay, one is about generating new example according to this distribution. So here I just generated 100 examples that follow the same distribution. So it means that none of these people exist, so to speak, but this data set is statistically similar to the other data set. It's kind of synthesized, new, plausible. So this, in that case, it's not very useful. This is actually not extremely useful. People do it for images. So nowadays we have neural networks that are extremely good at that, and you can generate fake people, you can generate fake anything. But you could use that to, I don't know, in a video game, generating content automatically. That could be an example. Besides that, it's not extremely useful. More useful, actually. Okay, now let's put this 1 second. More useful is to generate condition on some data. So here I say, the class is first, generate me someone that is kind of compatible with this first class. So it's literally conditioning the distribution on some values, on some variables. And this is pretty useful because it's actually missing imputation. So if you have, actually, you can see that because it's a numeric value, you have a negative age, which is not possible. So we do a pre-process. In that case, an automatic function should be able to be a bit smarter than that. In that case, it's not. In that case, we need to do pre-processing, like taking the log of the age or something like that. Anyway, so let's see that we have the age missing. So okay, let's see, that's and this person survived, just to make a change. This allowed to impute, that's a technical term, a plausible value given the other values. And as you see, it's actually random. It's conditioning. Oh wow, it's -15. Yeah, should have done a pre-processing. So it's conditioning the distribution and then sampling from this condition distribution. You can also get the mode. You can also do something like method mode finding, and this is gonna find the most likely value for the missing finding. Sorry. But a sample is usually better because you can do it several times, and then you can run your several imputed data through whatever pipeline you have afterward, whatever downstream application you have, and obtain histograms about possibilities depending on how the imputation is done. So it's very useful. Okay, another application of learning distribution is to compute the PDF of a given example. And this doesn't mean anything by itself. You have to compare it to other PDF. But let's say I have somebody that was 120 years old, and I'm asked for the PDF of that. And PDF is tiny here, 10 to the minus 316, as opposed to 10 to the minus 11 in that case. And this is used to detect anomalies. It's like, if the PDF is tiny, it means that this example is out of distribution. Like it's not where the data lives. Like in a way, this distribution is a model for where the data lives. Anyway, that's one way to do anomaly detection. Okay, I think we're done with automatic machine learning. So if you have any question about that, tell me, and otherwise we'll move on to neural networks. No question? Okay. You can ask question at the end as well. All right. So, neural network framework. Well, let's save. Yeah, I'm saving, so you can download the notebook. So, I mean, it's a lower level type thing than automatic machine learning function, but rather high level in its own category, as compared to other neural network framework like TensorFlow or PyTorch or these sort of things. This is quite easy to use, and you know, we have high level layers. We infer the type and dimension of the array. So neural network, okay, maybe I kind of assume people know neural network, but I should say a few words. It's kind of programs that have parameters inside of them. And generally, these programs compute arrays that, you know, to be more fancy, people call them tensors, although it's different for the physics tensors. So you have these arrays that are processed by the network, and then you have a loss function that you try
Etienne,
to.
can I ask one question? I feel that I have to.
Yeah, please.
What's the difference between this and physics tensors in that sense?
Oh dear, honestly, I won't be able to give you a good answer, even though I have a PhD in physics. So
okay, fair.
There's some properties. I was never into tensors during my, so I think people want to call it, the mathematical term, I think, for arrays is hollows, but I think array is pretty good. Anyway, people call it tensor now, it's fine. So just numeric arrays. And yes, so neural networks process these numeric arrays, and they have parameters. And basically, during the training, the training procedure is trying to turn the knobs of the parameters to make the network do the tasks that we want it to do. And we measure how well this network is doing the task by computing a loss function, a measure like accuracy. Actually, it's actually not the accuracy. It's actually this measure that I showed before on the learning curve. It is this log loss, people call it, or mean cross entropy, or there's many names, which is basically looking, let's say, I mean, I'm talking for classification here. I'm looking all the example in the training set, and I'm looking at what are the probabilities assigned to the correct class by the model. And basically you multiply these probabilities, and that's your loss. So we're trying to, I mean, you put a log and a minus sign to make it minimize, because it's usually the way people see it. You have to minimize the loss and not maximize an objective, but it's the same thing. So you try to have your model predict high probabilities to correct class, which makes sense. And usually they are set up in layers, and you have to define the layer, and you have to define the dimension of the type of data that is fed to the layer and the type of data that exists the layer. So, for example, the dimensions of the tensors / arrays. But this is done automatically. Also, you have to initialize these layers, so you have to initialize the parameters, but this is done automatically as well. Anyway, things like that. Data encoders, decoders. This is small code that pre-process and post-process the data, before, after the network, and we have kind of that included. So yeah, that's what it means to be high level. And yeah, actually, yeah, these sort of things as well, visualization. But anyway, let me show you instead of just talking. Okay, something I should mention is that there's MXNet on the back end. That's one of these main framework. Like, you have TensorFlow, PyTorch, and MXNet is one of them. And you can train on GPU, multi-GPU. Like, there's no performance compromise with these sort of things, because it's meant to be trained on large amount of data, large amount of images, text, audio. And so you cannot afford to have something that is not fast enough. It's as fast. They are all about as fast, actually. They all use the same internal libraries, all the main frameworks. So it used to be a time where MXNet was the fastest, actually. But now I think they're all the same. Okay, so let's define network from scratch. One way to define networks is to use what we call a net chain. This is the simplest type of network. It's just a chain of layers. So here I put a convolution layer. This is a nonlinearity. Actually, it's a shortcut for element-wise layer. It's a shortcut for this. And ramp is, often people call it rectified linear unit. It's identity when it's positive and 0 when it's negative. It's kind of put to 0 all the negative values. Pooling layer, another type of layer. All right, so that's our chain. And convolution layer, the sort of things that do a convolution, like its name indicates. So you have kind of a window that is parameterized, and that is scanning the entire image. So this is going to be a network for images. So scan the entire image and compute a linear combination, actually. Each time you compute a small linear combination, and you have many of this convolution kernel, as we call it. Okay, anyway, that's a very classic net that is like, I don't know how old, 30 years old, about, probably a bit more. And we're going to train it on MNIST. So that's why we have this decoder, which says we're going to classify, to predict a class, and the classes are all the numbers between 0 and 9. And the input is going to be an image of size 28 by 28 and grayscale. Okay, so let's get the training and test data. So, I mean, you already saw, oh dear, yeah, okay. Training digits, that's fine. You already saw this data set before. We have to define the network. This is called a LeNet. It's a French guy. It's Yann Lequin that invented it. He gave it a French-sounding name. And training digits. Sorry, it's not the right variable. So we just do net train of this network, put the data on a second argument. So a little bit of pre-processing. And here you go, it's training. So you can see another type of learning curve. Here, it's not the number of training example seen, although it kind of corresponds to that. It's just time. It's just so what it does is that there's several, there's 30,000, let me see, what is the size of this data set? Oh no, 60,000. Okay, there's 60,000 digits here, and what it does is it scans over all the digits several times, and it takes them by small batch of like 10 digits. We'll call it mini batch. So in that case, the batch size actually more, it's 64. So it takes 64 by 64, and each time it reads this 64 digit, figure out how good they are, how good the classifier is, or good the network classifies them, and depending on how good it is, changing the parameters. And yeah, so it's kind of an iterative optimization process, and you can see the loss going down. So when it goes down, it's good. Although I should have used a validation set here, because sometimes you are, in overfitting regime, which means that the performance gets better and better on your training set, but less good on your validation set, or on held out set that you're not training on. And this we don't want. We want to perform good on new data. We don't care about performing well on the training data. That's not the point. Okay, so error rate, yeah, okay, we're about 2% of accuracy. Okay, great. I'm gonna stop here. Stop the training. You have a network. You can look at it. Actually, a nicer way to look at it is to do a net graph out of it. Then we can see a little graph. Here you go. So you can see that's a convolution layer, and I kind of see what it is. This is a nonlinearity and so on. Linear layer, the softmax layer. Okay, let's just train. Not train it. Sorry. Let's just test it. And I don't want this one. I want the digit. Okay. So train net. So this is our test example. So this 5 was not in the training set. And yes, it correctly classified the 5. This task is not so hard. Even naive model get 95% of accuracy. We can get the probabilities, or the top probabilities, let's say. I think it's pretty confident. It looks like a good 5. All right. We can also do measurements, things like that. Trained net. Let's put the whole test set. And okay. Okay, so you can see the confusion matrix. So you can see it's very diagonal. There's 98.6, 98.7 almost % of accuracy. It's a rather easy task. The state of the art is 99.5 or something like that, or even more. Okay, let's have a bit of fun with this one. Let's look at this inside. Hopefully we have how much? 17 minutes left. Okay, I'm going to give it an image, and just look. Instead of looking at the result, I'm going to truncate the network. So this is a network that has 10 layers. Let's just take 4 layers. So I use net take. Net take, that's we call it surgery function. Things to modify your network. That's one of the aspects of this framework, is that you can manipulate networks in the same way you would manipulate a formula. So that's why we call it symbolic. Okay, so now this network, if I give it the 5, it's going to have a bunch of numbers. Like it's kind of what's happening in the middle. So to visualize that, I'm going to do image. Here you go. So you can see kind of the one slice, in the middle of the network, what it sees. And you know what? Let's do something fun. I'm going to put current image. Okay, let's see what it sees when I put myself. All right, great. And now I'm going to do it. Let's do current image, dynamic. This is kind of a, small video. And if I put this inside, it should, no, I'm going to put the dynamic around it. Whoop. All right. Now you can play around with your network. And it's not extremely instructive, but actually, yeah, it's a little bit instructive to understand how neural networks works, kind of. So these are more high-level features. If I net take, let's say 6, you should probably see a different, exactly. So now there are high-level features, and we don't see well. If I just take the beginning, actually, we should probably see, let's try to take 2. Okay. In the beginning, as you can see, it's too small, probably, for you to see, but it's still a lot about what the image looks like. It's not very semantic. Yeah, there you go. You can kind of see myself in the network. And as we progress in the network, information get less and less about the pixels and more about semantics, what is in the image. All right. Okay, I'm going to stop this up. Stop this dynamic thing as well. Okay, you can also specify things as a graph. So this, for example, is, so you would use net graph and you put a bunch of layers. These are linear layers, it's another syntactic sugar. And then you have to say how these networks are connecting with each other. Layer 1 is connected to layer 2, which is connected to layer 3, and so on. Layer 2 and 4 are connected to layer 5. So yeah, you play a little bit Lego like this. And that's how you define your network. Recently, we added another way. Yeah, question? I heard something. Okay. Recently, we added another way to create these sort of things, something we call function layer. We almost call it net function. Maybe we'll do a net function later. Anyway, so this is to define similar things, but with a classic program instead of, layers and then you connect them. Instead of this sort of graphical programming, this is like a regular, imperative type programming. And this is pretty nice. So this is the same thing, I believe. So actually, I can do a net graph. I can visualize the graph by doing this. Yeah, same network, but defined as code. Like it takes an input, and there's a linear layer, and there's a ramp, there's another linear layer, hyperbolic tan, multiply these two, add these two, that's what it is. And this way is actually quite nice to define networks. Honestly, it's actually better than that. Yeah, it depends for what network. Sometimes this can be pretty good, but many times the programmatic approach, I don't know if it's because we are so much used to program or because of another reason. I think it's a bit of both. Like, for example, this thing, which is actually a real layer that somebody had to do. And it amazed me because that's take a vector, take a matrix, dot product with some fixed parameter. Then there's this array of parameters. So this is more of a low-level thing, You're not using an existing layer. You're kind of creating yours by specifying the learnable parameters and the operation that are done with them and the input. And this one, so that's the graph. That's the graph, and that's how it looks with this sort of graphical programming. Like it's pretty hardcore, and that's how we would do it. I think we can remove the names, but then you have to put 1, 2, 3. You have to remember which their order and so on. So that's the better way to do with a graph, which is way worse than doing it with a function layer. So anyway, there's actually a global shift to everyone to program like that. That's why PyTorch is a framework that is kind of getting, eating market share from TensorFlow. It's because they were kind of the first. They were not the first, but whatever. There was the one that popularized this style of defining networks. Or rather this style. It looks more like that. This style of defining networks. So yeah, that's one thing we are working actively to really give this nice high-level, regular code way to define networks. Which I think, I don't think any framework allowed to do something like that. I'm not sure. This is pretty neat. Okay. All right, so that's how you can define networks. But defining networks is hard. Creating your own network is hard in a sense. Coming up with an architecture is hard. Like a usual question people ask about your network is, how do I know if I should use a convolution or this or that or this layer? How do I know the tricks? Well, it's pretty tough actually. So you can get a bit of sense. For images, you have to use convolution layers, general. There's some pattern, like this pattern, convolution, nonlinearity, pooling layer. This is super classic. Nowadays there will be a batch normalization. There will be, so there's some classic pattern, but it's much easier to just take a network that already exists for a similar task you want to do and just modify this network. And so that's why we have a neural network repository. Some people call it a model zoo. So we have about 120 network. Let me grab one. One network, this is a BERT network, which is a very classic network trained by Google to pre-process text. Nowadays, most modern natural language processing application, the text is pre-processed with this thing. And yeah, we can look at it. Actually, okay, this is going to be a nice example to show you how you can visualize networks. So you see here, you have kind of two nodes. And then I click that one, and this one has 12 nodes, 12 layers, kind of. But each of these layers contain many layers. It's kind of a Russian doll type thing, and it's nested. And I can click, or I can click that one, let's say. And you can always click to see what's going on. I think attention, yeah, attention is the main part. So you can see here the 12 attention head. Actually, I understood how this network was working. I mean, I had the paper, but how this is a transformer architecture. How transformer were working really by both having the paper and then using this as clicking in my way to understand. Oh, that's where the attention part is. Okay, let's look at the attention. All right, oh, that's this network. Yeah, that makes sense. So using both the paper and this was super useful to understand how this thing works. All right. I think that's one of our main added value. There are others, but to visualize networks like that. Okay, so let's actually use this in the 8 minutes we have left. Let's try to make it 3. So then you can ask questions. Let's use this repository to get the state-of-the-art latest network to recognize image in general. It's called EfficientNet, made by Google as well. Actually, and what we're going to do is to take this network. So this network recognizes stuff. Okay, so I can do current image. I think it knows about people. It doesn't know about everything. It's a little bit. I think it knows 1,000 things, which is not super high, but it recognizes 1,000 things very well. Actually, well, actually, maybe it doesn't know about people. I think that's what's happening because it's a good network. So it doesn't know about people, but it knows about many other things, and that's fine because we don't want it to know exactly. We just want it to know to recognize image in general. And then what we do is we're going to cut its head, so to speak. So we're going to truncate this network, basically just remove the last layer. I mean, the last 2 layers, the last linear layer. So let's take up to top dropout, or let's have pull, I think is good. Is that what I did? Okay, so let's do net take. Nope, the network. So what is it? I call it F, it's efficient net. And then, okay, let's remove this. And pull, oops. Okay, so that's our extractor. And this returns numbers, it doesn't return, it's gonna return 1,020, 1,280 numbers. And I'm going to extract, basically to compute these numbers for all the training examples, which by the way are our mushrooms. It's the same thing. So I'm transforming mushroom into vectors basically, but vectors that have a lot of semantic in them. It doesn't know about mushroom. I don't think this network knows about mushroom. I should test it actually, but it knows about many things. And so the feature we extract have a lot of meaning in them already. It's like, call it like semantic features. And then I'm creating a small net chain, just a linear layer. And I'm going to train this next chain on this small chain on these features. So, okay, it's very fast because it's a tiny network. We can stop it already. I think it might be overfitting otherwise. And now I'm joining the extractor and the head. So, okay, so I cut the network, basically. I retrain the last part, and I join them together. And I have a new network, and now we can try, I think it was test. So let's look at this one and this one. You got it correctly, great. And now let's do classifier measurements to see. And new net. and test. And it's actually perfect. It's perfect on a test set. I wonder, look, let's try on the original net if he knows about mushroom already. That would be, I didn't try that, so that would be cheating. But if he doesn't know about mushroom, that's pretty impressive. I mean, okay, that's good. So he just knows that it is a mushroom, but he doesn't know which mushroom it is, so that's good. Yeah, that's basically how you do transfer learning. You know, take an existing network, keep a part of it through the latest layer, and then retrain the latest layer. And this is kind of the magic recipe to train a neural network on a very small amount of data. I mean, very small, on a small amount of data in general. Like, if you have 1,000 images, that's better than 100, of course, and 10,000 even better. But without transfer learning, you need millions of images to get something decent. And Classify use transfer learning, but we're not using yet this network as a feature extractor, which we should probably do because it works great. Okay, we have 5 minutes left, so maybe I can use 1 minute just to show some applications. I mean, they're pretty easy to understand. You know, this is an application about object detection. So you just find where the objects are and you name them. This is an application about answering questions. So you have a text and then a question in natural language. How big was a dodo? And you try to find the answer. It's not making up text though. It's kind of selecting in the text where the answer is. Something that we train. So it's all things we train ourselves. Audio identify. This is, I wonder if I can make you listen. Okay, I don't know if you heard. I tried a little trick, putting my mic next to the speaker. So that was a bird, and he recognized it's a bird. And this is, by the way, this one for transfer learning is great. Like, we add state-of-the-art performance on some benchmark. We didn't publish anything, but we had state-of-the-art, you know, thanks to transfer learning. Okay, so and then there's text cases, which is really my favorite application. It's kind of try to extract whatever you want from a text. So, you know, I want all the mention of planet. And we should see from this Wikipedia page of planets, here you go. We could debate if Neptunian is a planet or not, but, and this works for 300 type of entity, which is something I haven't seen anywhere else. So, you know, I can also say I want the Mars, the planet, or I want Mars, the company, and let's see if it works or not. So Mars, the planet, of course, should be a bunch of mention of Mars. Yeah. And I showed the sentence, and Mark, the company, probably should not give anything. Here you go. It's kind of a Swiss Army knife for natural language processing. I love it. You can find topics, you know, find everything that talks about food, everything that is in French, you know, everything, yeah, person, email address, IP address, blah, blah, blah. And this is basically one big neural network plus a little bit of code as well. All the currency, I will all the currency from there, and please convert them to US dollar. So yeah, I think text cases deserve to be used. Okay, I'm not going to go further because I'm just 1 minute away, and I would like to answer at least maybe a few questions. Let me see everyone. All right, so any question? I guess, what are the classic questions? You're all at MIT, so you all have access to this? No licensing problem? You can export these networks. You know, we have an export to ONNX, which is a usual transfer format. That's kind of the classic question. Am I going to get stuck in Wolfram language? No, you're not. at least for neural networks. For my classifier, it's harder to export in something else. I mean, you can deploy to the cloud as we did, or you can, but yeah, convert it to another format might be not so easy.
So Etienne, maybe a question that I'm sure the audience is very interested in, but I would love to ask as well, is so kind of stepping away from just mathematics and the Wolfram language, talking about machine learning as a whole. You know, you spend so much of your time reviewing the latest stuff, implementing the latest stuff, thinking about it. Where any interesting things that are going to happen in the 2020s compared to the 2010s, right? The 2010s are like the emergence of convolutional neural networks and CUDA and GPUs and a lot of NLP in the last 3 years.
Yeah. Oh, I mean, a lot of things. I mean, okay, since you talk about GPUs, there's a lot of specific hardware that are done. For example, actually the Mac, the new Mac, there was an M1 CPU. They have like a neural network thing that is super good. They have a small neural core, I probably call it. And that is actually pretty good. Like it rivalizes with many GPU, not like high-end GPU, of course, but so I expect on that end, definitely some hardware. Probably not yet. 2010s was definitely about GPU. End of 2020s will probably be about specific hardware, I would say, for sure. Now, I mean, there's still performance improvements on image, still like so it's not over. It's not over. Image on like we have pretty good classifier, but you know, some people say it's not good enough for self-driving, for example. So it's still improving. Actually, the improvement, depending on the way you look at it, is not slowing down. Text, of course, is going to improve further. I mean, I assume everybody's seen this GPT thing, which is this massive model trying a huge amount of data. So I expect these big models to be much smaller and still achieve good performance. We don't see a slowing down in the improvement of things yet. Some people are predicting that deep learning will kind of reach. So it's really about, okay, can do many things with deep learning, but it's really about text, image, and audio, like principally about image, text, and audio. And some people say we're going to reach kind of a plateau at some point, and we'll need new things. We need to use systems that have logic in them. This one is more about intuition. It's not really about logic. Neural networks, you know, it's like, you know, the way you see that something is a cat, you don't really reason in a logic way, you know, it's because I did. You just know it's a cat. It's like an intuitive thing. There's actually some work to try to have neural networks go into this more logic reasoning side. And Transformer, actually this new architecture that I was showing you, but is a little bit a candidate to achieve that. It has this attention mechanism. And so it can really focus its attention, so to speak, which does mean that in this bunch of numbers, it computes focusing on only of these numbers. And by that, it can kind of do some manipulation, a bit maybe symbolic manipulation. So there's some hope that this stuff can start tackling tasks that need more symbolic reasoning machine. So some people say we'll have to do sort of hybrid symbolic system and neural networks to tackle these things effectively. I wouldn't be so surprised actually that there's some symbolic merging in the next 10 years with neural networks. That would be pretty cool. I mean, maybe it's already happening kind of with transformers, but not quite. So yeah, I mean, I don't expect to have artificial general intelligence, as people call it, in the next 10 years. I don't think it's good. I mean, first, it's not really well defined. So human-like intelligence, even like humans have so much input from everywhere. You know, like all our childhood, like, you know, we see, we listen, we like, you know, we look at art, we do so many things, and that's kind of this huge diversity. The amount of stuff we see is actually not high. Like neural network for images now are trained on 300 million images. I mean, EfficientNet has been trained with 300 million unlabeled image. Us human, we don't see 300 million images in our life. But I think the diversity that we see, and so that's why I don't think we'll have in the next 10 years. It was the next 21, the next 10 after, who knows? But anyway.
Very, very interesting. And actually, I think maybe, if it's okay with you, that might be a good segmentation into my talk that was kind of inspired, I guess, by a lot of our time sharing offices and talking about these things. And, you know, maybe perception is just the first step in a bigger system that needs to happen to solve real problems, and kind of this narrow AI versus, I guess, the public promise of more general AI.
Yeah.
Etienne, that was a beautiful talk. And every time I
Thanks,
hear you,
Greg.
I think of all these new things I want to try. So thank you very
Cool.
much. You probably can't see everybody clapping, but I'm sure that they're
Okay.